Problems in fluids 1, problem number 8. Assume you are designing a water tower of spherical shape that can contain 6 times 10 to the 5th kilograms of water. What's the radius of a sphere that will contain this amount of water? As you begin to work the problem, you know the volume of the sphere is 4/3 pi r cubed. Density is given by mass per volume. When you solve for this, you find the radius of the sphere to be 5.23 meters, and I will leave that to the student to solve. The second part of the problem, B, is more interesting. This is the A part, B. B says in a typical water tower, the shape of the sphere, the bottom of the sphere would be 40 meters, 120 feet above the ground. What would be the faucet pressure in a house located at ground level? Assume the tower is vented to the atmosphere, so we might have a hole in here, and ignore the difference in atmospheric pressure. So we're assuming the atmospheric pressure here at the top of the tower is the same as it is at the house. Since they differ by only 40 meters, that's certainly a very good approximation. The first question is, what is the height of the water? Well, the tower itself is 5.23 meters in radius. So this would be 10.46 meters from the top of the tower where it's vented to the bottom, plus the 40 meters would be the distance down here to the ground. So when we use H in our equation, this would be the total height of the water from the top to the bottom. So the pressure at the bottom is the density of water times G times the height of the column. The density of water is 1,000 kilograms per cubic meter. G is 9.8 meters per second squared. And the height is then 40 meters plus 2 times 5.23 meters, which we showed above. And this gives us a pressure at the bottom of 4.945 times 10 to the 5th pascals, newtons per square meter. Let's make sure our units are correct. I have kilograms per meter cubed. I have meters per second squared. And up on top for the height, I have everything in meters. So I have meters squared over meters cubed, gives me 1 meter on bottom. I have kilograms and seconds. So canceling out just one of the meters, I have meters squared on bottom, and I get kilogram meter per second squared over meters squared. That's a Newton per square meter, and that is the definition of the Pascal. Getting the correct number of significant figures, then I get 4.95 times 10 to the 5th, 495 kilopascals. What is that in pounds per square inch, which might be a little more useful to us? Well, I have 4.95 times 10 to the 5th pascals. How would I convert that to pounds per square inch? Well, I know atmospheric pressure is 14.7 pounds per square inch. Atmospheric pressure is 101.325 kilopascals. So I have atmospheres here over atmospheres, so this is really just multiplying by 1, but it does give me the units I want, and that gives me 71.7 kilopascals cancel out, or pascals cancel out, and I'm left with pounds per square inch, and I get 71.7 pounds per square inch. If you had this actual pressure at your house, that would not be very good, since it would destroy a lot of the equipment, the water heaters and everything. So what you actually realize at your house, because there are not just one house, but several houses on the line, that reduces the actual pressure you see. And most of the time you would expect about 40 to 45 pounds per square inch. If you get as much as 60 pounds per square inch, that usually is a problem and destroys something in your house. So while this is the correct answer to the problem, realistically, a house does not see that much pressure because there are a number of houses on the line, and they pull out the water and you don't realize the full pressure.